So we already talked like a lot about like graphs and like graph databases themselves. So I kind of want to not follow that path directly, but I want to talk about like how we can deploy them. And maybe just question up front, who has heard about Mesos or who has even used Mesos or Dcos before? Wow, that's a lot of people. Who has used Neo4j on Mesos or Dcos? One hand. I hope one hand, yeah, at least. Okay, so that's what we're going to talk about here. And to start out, I'm Jörg. So I'm working as a distributed systems engineer and developer advocate at Mesosphere. So that means I'm mostly coding on here, my shirt, Apache Mesos, or I'm like around giving talks, developing demos, talking to those guys as, for example, Neo4j, to get like more partners involved in this ecosystem. And so this is actually also how we got this idea for this talk. And first question, we actually need a cluster. So Neo4j also runs kind of decent on like one box. We can already do quite large graphs in like a single box. And so the cool thing about Neo4j is actually that we can cluster for both like high availability, but also for like those replica servers where we have read replicas for specific use cases. So those of you who might not have seen that yet, so Neo4j, it has like a core clusters, core servers, and they're actually in the current version, they have like synced writes. So they're like also read write here, and they're going to have one elected leader who is kind of like the server in charge. And then around we can create a bunch of read replicas which are only there to basically read data. And the cool part about it is I can have dedicated read replicas for specific like purposes or topics. So they'll be optimized for example, for reporting and analytics. I can have other read replicas targeted to specific query types. So I can actually, by utilizing multiple cluster nodes, I can really efficiently have answer like all/most of my queries throughout my cluster. And so this is like one use case where we need a cluster. And then of course the question, how can we actually manage this kind of like large scale cluster? When we as Mesosphere, when we look at clusters, what we often see is kind of like a static partitioning across different workloads. Imagine, so what we would, for example, we would see like 4 servers being dedicated to Neo4j, and this doesn't necessarily mean 4 physical servers. This can mean like 4 virtual servers, or yeah, 4 instances basically reserved for Neo4j. Then we have another subpart of our cluster which is dedicated to Kafka. We have one subpart of our cluster which is maybe dedicated to like a second Neo4j cluster. So this might, for example, be the test cluster which some other team is running. We might have a bunch of microservices. We might have something, as we heard about before, we might have Apache Flink running there. So we actually, what we end up doing is we end up subpartitioning our cluster into like a number of smaller subclusters, each dedicated to a specific like service or a specific framework. And this actually has multiple disadvantages. The first one from an operational standpoint is that I actually, as an operator, I really have to take care a lot about like moving stuff. So for example, what happens if one of those Neo4j nodes, like my main Neo4j cluster, is failing? Then as an operator, I would have to go in, move over one node for example, from the Flink cluster. And so it would actually involve like a lot of manual work. The second big disadvantage of this model is that we actually end up with very bad resource utilization. So usually those clusters, they end up at resource utilization somewhere between 50 and 20%, because each of those subclusters, so my Neo4j subcluster, my Flink subcluster, I have to basically provision them for like the highest load around. And so I'm actually doing normal operations, I'm wasting a lot of resources. So the target image where we would actually like to go to is this here, where we kind of We don't care about so much individual machines. We treat our data center as like one big box, one big pool of resources, and there we simply deploy all those services. And I, as an operator, I don't care too much on which particular node, for example, Neo4j is running. As long as my cluster is up and running and healthy, the system should take care of this. And this picture is exactly the reason why Apache Mesos was originally developed. We're going to see a bit about the history in just a second, but basically this ease of operational use. So how can I deploy like my large compute clusters? How can I deploy multiple Neo4j instances? This was like one of the main reasons, and second reason is basically increasing resource utilization throughout my cluster. And if we just briefly go back to this image, like one of the main drivers, in my opinion, why we see the increasing need for such kind of system as Mesos is that actually here the number of frameworks, the number of systems which actually would like to own, which would like to have their own subcluster is increasing. Like nowadays we have Spark, Flink, Neo4j, so there are like a lot of frameworks, there are a lot of subclusters I could potentially create, and so it becomes very like unfeasible. Back in those days when we just had like Hadoop there, one system which wanted to own the entire cluster, that was still like kind of okay-ish, but now we have like a lot of different systems wanting to own a cluster. It's not as okay anymore. And the way Mesos actually doing that is by this fancy term called two-level scheduling. And two-level scheduling basically refers to that we have Mesos on the one hand basically just dealing with resource allocation, and then for particular frameworks, so basically for each of those frameworks we saw on the left side, we have a scheduler. So the scheduler is basically like this component which is controlling which resources are used in the cluster, how do I react to when one of those nodes is failing. And actually there's even a default scheduler. So for example, for the Neo4j example, we will see in a second, we didn't have to write a scheduler, but there's like a default scheduler I can simply use, which will take care of that, scheduling my stuff, restarting stuff if it failed in the cluster. And this is actually done, and this is like symbolizing this two-level scheduling as well, because here in the middle, this is basically like the Mesos layer. This is the Mesos abstraction layer, which is abstracting the schedulers, which here I have like the Marathon scheduler. Marathon is the default scheduler I was talking about. And then this, for example, could be a dedicated Neo4j scheduler. This could be a Spark scheduler. And so they're basically separated by this layer of Mesos, by the Mesos masters, from the underlying node, from the underlying hardware. So actually those schedulers there, they don't see the entire infrastructure. They basically only see the subset which is provided by the Mesos master. And that makes it actually very flexible and independent to failure. So if one of those nodes fails, basically the scheduler can restart it on another node and the application can continue running. Also, just to have the complete picture, also this master level, the Mesos master level is highly available. We have a zookeeper quorum, which basically always makes sure that we always select like the leading master, similar to like this, yeah, so we have basically multiple standby nodes if one of the masters fail. The history is actually, it's also kind of interesting. So it actually originated as a class project at UC Berkeley, and that's actually the same lab where Spark was initially invented or developed. And Spark was originally actually developed as like a demo framework to show how easy it is to write distributed systems together with Mesos. And then what actually happened, those students who were developing that at UC Berkeley, AmpLab, they actually gave a tech talk at Twitter. And Twitter, if you remember, had like all those issues like this fail whenever the infrastructure couldn't cope with all the users. And so they actually were really happy about it. And they, which in my opinion was a really cool decision, they also decided to actually make it an Apache open source project pretty soon. And so in 2010, it became an Apache incubator project. And I believe about 9 months later, it was like a full top-level Apache project. And then the last step on this slide is basically Dcos. Dcos, as we're going to see, is another open source distribution of Mesos, which basically brings like all this stuff around, which makes it easy to deploy and which makes it easy for like other frameworks, as for example Neo4j, to integrate there. I mentioned almost all of this, maybe just those for reference, like who's actually all using that. Twitter is heavily based on it. Airbnb, whoever booked his Airbnb while staying here in Brussels has seen that. PayPal, Netflix, and actually anyone who ever used Apple Siri also has used Mesos underneath. So when we're talking about databases, of course, we also have to talk about storage. And there are different kind of applications or different kind of data applications, and all of them, they have different needs for storage. So the really easy part, this is basically on the top, this is like those front-end or non-persistent applications. If I have my Node.js application, which doesn't have any state, I have my Nginx, which doesn't really have a whole of state or none, then I don't really care on which of those nodes is restarting. Imagine my Nginx server is failing. I don't care where it's restarting. It can be any node as soon as it's coming back up quickly. If I'm having a database, as for example, Neo4j, it's slightly different, right? Because there I actually have state, and there I actually end up with two different kinds of models. So there are databases as Neo4j, which are really written for this kind of like distributed ecosystem already. So what they have is what we saw like on this second slide. They have like inbuilt replication, so they can actually survive a single node failure, or potentially multiple, depending on how many replicas you have. But there are also other databases. So if I take like a standard MySQL instance, like a single MySQL instance, this won't survive like a single node failure, but then basically all my data is going to be gone. So for actually both those models, we have different storage opportunities inside Mesos. So for the models as, for example, Neo4j, which already have this inbuilt replicas, we have something called local persistent volume. This means you're going to get fast storage, which is directly attached to the node. It's just going to be the hard disk, flash drive, SD inside the node. And I can really use that quickly and fast as I would use a normal disk. And the nice thing is, whatever happens in the cluster, when that node fails, when Neo4j, the instance is failing, whenever it comes back up, I still get all those resources back, so I can keep on running on that particular node. If I'm on the other side and I'm running something like this old-fashioned MySQL, then it's slightly different, because in that case, I cannot survive a single node failure, and I want to make sure that I can restart on any node in the cluster, because if that node is failing, I need to be able to retrieve my nodes. And that's where we actually have external storage, which helps us to be able to restart on any node and basically retrieve that distributed storage. If I'm something like Neo4j, I don't want to use distributed storage, because in that case I would have distributed I/O on like two levels. First inside Neo4j, the database for each replica, and then again on like the storage layer. So if I already have that layer inbuilt, I don't want to use it. Dcos. So as mentioned before, Dcos is basically distribution around Mesos. So it basically comes with like all the features, service discovery, load balancing, comes with a nice UI, which we're going to see. So it actually, it helps me to deploy it, because I don't have to worry about like all those nifty details. It basically, it comes all out of the box. I can install it on-prem. There are packages available. I can install it with cloud templates. So I can actually also choose where I want to run it. This is the UI, which we're going to see in a second. And maybe just more important, as we're talking about particular applications, we have this cool thing called apps. We have basically the App Store for your cluster. So here you can go with like one click, you can install Spark, Kafka, or actually also our different Neo4j packages. And as I have some minutes left, I would actually just like to go to my cluster and show that. So here I have my cluster running, so that's basically it's running on a cluster in Amazon, and as we can see, my components are healthy. And what I actually did already, because it takes some time, I installed the Neo4j core service. If we go to this Universe App Store, we have multiple packages available. So Neo4j, how readable is that? With the beamer, kind of okay? Okay. So actually in this App Store, we have 3 different packages available. So the first one, it's the core package, and what that will do, and what I already done, it's basically going to go and install Neo4j inside my cluster. So inside my cluster means that a typical Dcos cluster, it has internal nodes which are not exposed to the outside for security reasons, and then there are external nodes. So the typical pattern, which we're also going to do here, is basically on those publicly available nodes, we're going to install a proxy, a load balancer, and that's then basically going to proxy into my cluster to my particular application. And that's something which I can do right now. So I'll go here and install my Neo4j Proxy. Cool, it's been installed. If we go back to dashboard, we actually see is here my CPU allocation is slightly increasing. Also, slightly my memory allocation, it doesn't take too much memory. And I actually now also have four tasks running. So it's going up. If I go in here, I actually see I have now my core and my proxy running. And let's hope that it's really running and available. So this is a public node. And yes, here we go. Let me just double check that I'm not using Bolt. Yes, because we are dealing with Amazon and like internal IPs. I unfortunately cannot use Bolt from the public, from the proxy, but that's all configured nicely. And let's have a look at our cluster. So what I can see here, I now have 3 nodes available in my cluster. So I have this one lead here, and I have the followers. And what we actually can also do in a second, we can try to kill one of them and just see that it stays up. But what I want to do first, I want to go back to the universe and install like the third package we saw before, which is the read replica. So we are installing those read replicas. Let's look again on the dashboard. Yes, this takes more CPU and memory, so it's starting up. And currently it's still unhealthy. And if we take a look here, we can actually follow what's happening. So they're actually running, but they have health checks defined. And those health checks, they're like an important measure because they tell multiple components within the system which parts can be used and which not. So for example, if one of them is unhealthy for a number of time, this is a signal to the system, maybe I should restart it because it didn't really work as expected. So in that case, the system would go and actually restart this one instance which is not healthy in this case. Also, load balancers. So for example, if I have a load balancer up front, it would, and it's a smart load balancer, it would only use those instances as backend which are currently healthy, and hence only go to the healthy ones. So if we go here, and we reload, we actually now see here we have 2 read replicas. Cool. Actually, but now we need even more. So now I can actually just go here and let's scale them up. So I can actually do all of this, what I'm doing here in the UI. I can also do all of this via API endpoints, via REST API. I can do all of this also from a CLI. And now we're just deploying like our third read replica. Currently it's stating, hope I have enough resources left. Yeah, and now it's running, and hopefully it's also going to be healthy in just a second. This is what it's still waiting for. And once that's done, we also are going to see it in the Neo4j tab. Let's reload here. Yep, there is our third read replica. now let's actually just go here and kill one of them. So kills, it could either be some error happened, my application was killed because it was using too much memory, it was there was a programming error inside and it's just crashing, and so my one instance is gone. Kill. And we actually didn't really, that was so fast, because so we didn't really see too much, but what we can actually see here, updated a second ago. So as soon as one of those instances dies, the system is going to recognize, and the system basically tries to keep this invariant that there are always 3 instances running, and so it's going to go there and actually restart one of them. Wait, yeah, and there it's restarting. Cool, but this kind of isn't too cool yet. So what we want to do is we want to run some stuff on it. And I hope this is, yeah, healthy, good. And so what I prepared here, as mentioned before, we have also CLI support. And I'm just going to show you a short app definition. This app definition is basically how the system can be told to start something. And this is actually using the Neo4j Twitter load. So it's a load generator, like artificially generating Twitter data. And so I'm going to post that to the cluster in just a second. Just one nice bit I wanted to point out is actually how we can address those servers within the cluster, right? If I'm writing such kind of app definition, I don't know where it's running in the cluster, and I don't want to hard code that in my app definition. So what I actually do, I can use service discovery names. So in this case, it's a virtual IP, named virtual IP. And no matter where that's running in the cluster, I can always reach it under this address. So in case this is actually also a load balance address, so if I have multiple backends, this address is going to load balance to anywhere in my cluster. And this is like quite useful because I can just hard code that from within my application, and I don't have to particularly care where the other application is running in the cluster. So app add. And I could have done the same now from the UI. I could have just copied it here. I could have done the same, posting it to an endpoint. And now we actually see it's alt staging. This usually means it's holding the Docker container. In production use cases, you would have like all your Docker images in a private registry within your cluster. For this demo purposes, I'm using the normal Docker hub. So actually the Docker polls, they take a while. But seems to be deploying. Seems hopefully to be deploying. Staging. Demo goals are not nice to me. Yeah. Let's see what's happening inside Neo, whether data is actually pushed in. No, I'm not seeing my notes yet. Yeah, but it's failing containers. So let's do live debugging and figure out what's wrong. So I can now actually just go here and check the standard error. No write operations are allowed directly on this database. So he's not finding the leader for one.
That's good. But the system for shows one leader, right? In the system for you see one leader, right? Or did you kill too many of the core servers?
Yeah, I hope.
You probably killed too many of the core servers and then you can't fork for.
Oh, I see one leader.
Can you refresh that? If it's
okay. So I'm gonna just debug this after this talk, but basically what we would see is basically So it's app definitions. They're a really, really easy way to deploy applications talking to Neo4j. If I would find the leading master right now, which I'll just figure out after the talk what's wrong there, why it's not deploying. But this is why we actually see this keeps on restarting and failing because it can't talk to the master. Nice part is what we could see that it's kind of easy to figure out because we have an easy way to get to the logs. I don't have to figure out now here, and we can actually see it's running on different servers. So I can actually don't have to worry about like on which server this instance is running now. I can simply go there and figure out what's wrong here. Why isn't that running? Okay, that would actually bring me back to almost my last slide. And yeah, this would have been the demo. We would load like our Twitter data and actually see that it's running the cluster. What we then can actually do, we can create different read replicas for that and basically scale up and scale down the cluster as we did before. And yeah, this actually brings me to my last slide. Whoever wants to try that out, the code is available online. Feel free to play with that. And the packages are also available whenever you install Dcos anywhere. So feel free to play with that. And actually, as it's open source, feel free to contribute and give us feedback what we can improve there.
Okay, cool. Thanks a lot. Any questions for you?
Okay, well, a short question. One is, since 3.1, Neo4j has two types of clustering. Is there a reason why you only presented one of them?
What do you mean one?
You have the Colville clustering and you have the high available.
So we have both running. So
no, it's only core clusters because the setup of coastal cluster and all the self-discovery of a coastal cluster and smart routing and so on is only coastal clustering. And going forward, HA will go away and so on. Okay.
But
okay.
Yeah. I see different role on the do not comply with the DB Mesos setting in the config of Neo4j.
Oh, you mean?
Followers setting?
No, followers is replicas, and it was just the output of the UI.
Okay. It's basically you can name it as you like.
Replicas and leaders. Oh no, core servers can have two roles. Core servers can be the leader or follower of the core. In general, if you see that, it should be one. So one of them is the leader in the core, and the other ones are followers.
So here.
It's an automatic setting, so they fail over to. So the leader coordinates the RAF, the commit, and the class membership.
Thank you.
Any help with the performance diagnostics, like I don't know, with the performance problem, like swapping or something like that?
So you mean in particular of Neo4j or in general of like the overall system? Okay, Neo4j would actually forward to you if that's okay. And for Dcos, we actually have metric endpoints. So basically, and this is also where something like the application would integrate. So that basically, if you output your metrics on like a dstats endpoint, the system's going to pick it up, basically aggregate that, and you can actually see this is belonging to Neo4j, this is belonging to that particular cluster, and so basically see all those performance statistics together. On like both system level. So for example, what we saw there is like the allocation. So I'm saying I want to give my Neo4j read replica, it should have most have like 2 GB of RAM. And so one thing which you should always monitor is like how much is it actually using? It's always using like 1.99 and you're really close to being killed, or are you actually using much less than your wasted resources in your cluster? And
for Neo4j, that means that we still have to add to the package or to Neo is to support like this is the output, and then for Neo4j has built-in metrics quite a lot. We just have to build the connector that writes it so that Mesos can then read and display There was another?
I'm not sure who was first, but yeah.
what happens when a leader dies? Because you don't keep the data, right? So is it like a replica began a leader, but when the leader comes up, as you're in the Docker, you load the data, so is there some balancing automatic done? Or?
So you mean if one of those core servers is dying? So if one of those core servers is dying, one of the others would take over, and the system first keeps on running. But you mean how is the data recovered?
Yes.
Or, so basically this one is gone, what's going to happen? So what's going to happen kind of depends on how you have different configuration knobs. By default, what's going to happen is he will try to put it back on that server. And then you can also specify, like, after a while, you should stop that and go somewhere else. So basically you can define this behavior, this failover behavior, what should happen. But as we're talking about distributed systems, often what's happening actually is that you have like a short network partitioning between some servers, right? Because network is so reliable. And so usually you want to wait for either that server to rejoin completely, or if it's just like a task failure, if just the core server task has failed, you want to wait until it's restarted, which we also see what would happen. And in that case, as being restarted on the same node, by default, he's going to pick up his data again.
Yeah. And for Neo4j itself, if you start a new node of the cluster, and a new instance in the cluster on a blank machine, and it just gets the data from the other machines of the cluster and then continues to go. Last question.
How are you doing load balancing in Dcos? Are you using round robin or something else?
So depends on the method you're using, right? So what we saw with the virtual IPs, you can configure that if you know like certain endpoints. It's quite hidden, but you can select your method. And for the other load balancing, for which we call like external load balancing, which basically is an HA proxy, you can also configure your HA proxy load balancing method. Yeah.
If you use a replica and for internet connection is on, then I continue to input data and synchronize later.
You mean with the read replica? So
the read replica is really just a read-only like a cache instance. So you can have a large number of these, but they're not. You can't write to a read replica. So you can write to nodes in the core, but only if you have a write quorum. Otherwise, you have to buffer the input in a queue or something like that.
Yes,
so,
but do you have a solution for that? Because on a replica, I need to be 24 hours up anyhow,
so,
even if...
No, the replica itself, each replica is just a throwaway instance, so it doesn't have to be up, so it can be killed and then will be new replicas started. Of course, the replica doesn't really have an identity or something like that, it's just a machine of the cluster that provides data. So you can't really say, I want this instance to be up, because it will just restart instances as it needs to. And what I could imagine what you could do is on the like load balancer level, if the server is in a, for instance, partition split mode where there's no write majority, that you queue up, for instance, requests in the load balancer until the core has healed the partition, and then it will continue to write back the but that's a good point. So we will make sense to provide some like documentation on how to set something like that up, so that you can have an application that sends events to the cluster, and then it can replay and recover events after the partition has healed.
Yeah.
So that's a good
that's
actually.
Just in general that problem of any distributed system, right? Yeah. So yeah. Cool. Thank you very much.
Thank you, everyone.